In the previous video, we saw the thread synchronization with Q. Here we are at the last video of this section, evaluating the performance of multi-thread applications. In this video, we'll perform a total of 3 tests, and for each thread, we will use a different function. The GIL, as described in the previous section, is the lock introduced by the C Python interpreter. The GIL prevents parallel execution of multiple threads in the interpreter. Before being executed, each thread must wait for the GIL to release the thread that is running. In fact, the interpreter forces the executing thread to acquire the GIL before it accesses anything on the interpreter itself as the stack and instances of Python objects. This is precisely the purpose of GIL. It prevents concurrent access to Python objects from different threads. The GIL then protects the memory of the interpreter and makes the garbage work in the right manner. The fact is that the GIL prevents the programmer from improving the performance by executing threads in parallel. If we remove the GIL from the C Python interpreter, the threads would be executed in parallel. The GIL does not prevent a process from running on a different processor, it simply allows only one thread at a time to turn inside the interpreter. The next code is a simple tool that is used to evaluate the performance of a multi-threaded application. Each test calls a function only once in 100 loop iterations. Then we'll see the fastest among the 100 calls. In the for loop, we call the non_threaded and threaded functions. Also, we iterate the tests that increase the number of calls and threads. We will try with 1, 2, 3, 4, and 8 at the end of calls threads. In the non-threaded execution, we simply call the function sequentially the same number of times corresponding to those threads that we would use. To keep things simple, all the measurements of the speed of execution are provided by the Python's module timer. This module is designed to evaluate the performance of pieces of Python code, which are generally single statements. The code used is as shown. We've performed a total of 3 tests, and for each head, we use a different function, changing the function code function_to_run function defined in the sample code. The machine used for these tests is a Core 2 Duo CPU, 2.33 GHz. Let's carry out the first test. In this test, we simply evaluate the MC function as shown in the code. It'll show us the overhead associated with each mechanism that we're testing. Let's test this code. Open your command prompt and navigate to working directory. Run the Python file. If we look at the results, we see how the thread calls are more expensive than the calls without threads. In particular, we also note how the cost of adding the thread is proportional to their number. In our example, we have 4 threads with 0.000301 seconds, while with 8 threads, we employ 0.000603 seconds. We will now carry out the second test. A typical example of threaded applications is the processing of numbers. Let's take a simple method to calculate the brute force of the Fibonacci sequence. Note that there is no sharing of the state here, just try to include more tasks that generate sequences of numbers. We will then make some changes here. Let's run the output as shown. As we can see from the output, we get no advantage by increasing the number of threads. The function is executed in Python, and because of the overhead for creating threads and GIL, the multi-threaded example can never be faster than the non-threaded example. Again, let's remember that the GIL allows only one thread at a time to access the interpreter. Here's the third test. This test consists in reading 1,000 times a block of data, 1 kilobyte, from test.data file. The function tested is as shown. These are the results of the test. We've begun to see a better result in the multi-threading case. In particular, we've noted how the threaded execution is half time consuming if we compare it with the non_threaded one. Let's remember that in real life we would not use threads as a benchmark. Typically, we would put the threads in a queue, pull them out, and perform other tasks. Having multiple threads that execute the same function, although useful in certain cases, is not a common use case for a concurrent program unless it divides the data in the input. In this section, we have seen the use of the Python threading module followed by how we can define and determine a thread. We then saw the use of a thread in a subclass. Later, we carried out the thread synchronization with lock, rlock, semaphores, condition, and events. Further, we saw the use of with statement and carried out thread communication with queue. In the end, we saw how to evaluate the performance of multi-thread applications. In the next section, we'll see the process-based parallelism.